Every half minute, somewhere in the United States, there is a destructive fire. Every half minute, a fire that will maim and injure, destroy lives and property. This film is designed to help you prevent fires and to point out a few little-known facts about materials you use and handle every day. Most materials will burn readily if allowed to get hot enough to give off combustible vapors. For instance, building lumber will give off vapor at approximately 500 degrees. This temperature can readily be reached by friction with a dull cutting tool. Cotton used in bedding, drapes, and clothing will produce combustible vapors at even less than 500 degrees, less than the temperature near an electric heater. Plexiglass used on airplane cockpits will emit combustible vapors between 300 and 450 degrees Fahrenheit, a temperature range resulting from air friction as a plane approaches the speed of sound. Fuel oil used in large quantities aboard ship will give off vapor which is combustible at temperatures as low as 150 degrees. So-called safety solvents used to wash machine parts in engine repair begin to vaporize at 100 degrees Fahrenheit. Gasoline and jet fuels vaporize at temperatures as low as 45 degrees below zero. However, before these vapors can be ignited, they must be mixed with air, and this mixture must be within certain proportions, not too rich, not too lean. For example, gasoline vapors will not ignite if this small amount of gasoline were mixed with more air than could be in this balloon. Neither would this same amount of gasoline ignite if it were mixed with less air than could be contained in this balloon. This explains why this spark, directly on the surface of the gasoline, will not ignite it. The vapor-air mixture on the surface of the liquid is too rich. It also explains why a spark at some distance above the beaker will not ignite the mixture. At this height, the vapor-air mixture is too lean. Now, watch when the spark occurs at a point where the vapor-air mixture is within its combustible range. Ignition could have been accomplished just as easily here, at the side, since the vapor is heavier than air and will flow for great distances, much in the manner of a liquid. This gasoline-soaked rag will help illustrate this for you. The vapors evolving from this rag will flow down this tube. A candle placed under the bottom of the tube will cause the vapor to ignite when it reaches the flame. By smothering the fire, we can see the smoke-filled vapors again running down the tube. If a spark or flame is brought in contact with the vapors, combustion will again take place. Many accidents occur because people do not realize that gasoline vapors are heavier than air. One such accident occurred to a man who, even after 15 years of experience with gasoline, apparently failed to realize this. This man was accidentally splashed with gasoline. Instead of letting the gasoline vaporize out of doors, he decided to change to dry clothes. Several other men were in the locker room. They started to chat. Instead of changing immediately, the man delayed. Meanwhile, his gasoline-soaked clothing was giving off vapors in the enclosed room. An open-flame heater was in use in one corner of the room. As the gasoline vaporized, it mixed with the air in the room and drifted down toward the heater. It took his life as well as the lives of 3 other people. carelessness, ignorance, call it what you will. The end result is all too often tragic, even though it all may have started as an everyday happening. A sweater needs cleaning, and of all things, gasoline is used. Someone falls asleep. A cigarette is accidentally dropped. A lighted match is carelessly thrown away. But an open flame is not the only cause of costly fires. They can start from many other sources. An electric heating coil can start a fire. The spark from a switch. A running electric motor. The sparks, no matter how tiny, will ignite the gasoline vapors just as easily as a direct flame. A light bulb burning in the presence of combustible vapors can be a fire hazard. This hot bulb will break if a drop of water or perspiration falls on it and ignite the vapors. For this reason, explosion-proof fixtures are required in areas where flammable vapors are present. Static electricity is also a source of ignition. The static electricity generated by merely separating this piece of metal from this piece of plastic is powerful enough to light up this neon tube. It will also explode the gasoline and air mixture in this tank. Sparks from welding or cutting equipment coming in contact with combustible vapors will start a fire. Spontaneous ignition is another fire hazard. It can occur in connection with many materials commonly used in the home: vegetable oils, polishes, and waxes, grease and oil-soaked rags, paints, and paint cleaners. To illustrate spontaneous ignition, let's put some vegetable oil on a rag and place it in a locker. The vegetable oil will oxidize, a process that generates heat, and in time, the rag will smolder and burst into flames. This model house will help to demonstrate another frequent source of fires in the home. Here, clothing placed near a hot air vent becomes a potential source of a fire. The heat from the vent raises the temperature of the clothes on the dryer to a point where they give off combustible vapors. Even the best of the electrical safety devices sometimes fail and may indirectly become a source of ignition. Here is a good example. This is an electric iron with a thermostat that failed. It caused the iron to overheat, melting its stand and fusing it to the iron. As the iron became hotter and hotter, it set fire to the combustible materials with which it was in contact. Many fires have been caused by overloading and short-circuiting. Three-way and five-way plugs encourage overloading of circuits. Flexible cords, which have become frayed, eventually result in short circuits. In violation of safe practices, wires are often stapled, tacked, or taped to walls and woodwork, or placed under rugs, where constant wear will in time damage the insulation, causing short-circuiting. With our model house, we can demonstrate this. The lamp cord leading under the rug has been damaged, and the wires are overheating due to a partial short circuit. This could be the beginning of another serious fire. Why doesn't the fuse blow, you may well ask? The answer is the fuse itself requires time to overheat and melt, and thus shut off the current. During that interval, the wiring also has time to overheat. We can prove this with this equipment. which contains wiring circuits designed for 6-ampere loads, a fuse, and a circuit breaker to protect the wiring from overloading. We'll first operate the system with this circuit breaker, which is rated at 6 amperes. These lights draw a load of about 4 amperes. We can increase the load with this rheostat, right up to 6 amperes, the rated capacity of the circuit breaker and the wiring. Now let's plug in this soldering iron, which adds further to the load. In fact, the load is now twice the rated capacity of the circuit breaker. And still, the circuit breaker has not tripped, although the wiring is now overheating. This short length of bare wire, which is part of the wiring circuit, gets hot enough to ignite a piece of paper before the circuit breaker trips and shuts off the flow of current. Watch. Now let's operate the system through the fuse. Rated capacity 6 amperes. We'll plug in the soldering iron to give us a load of almost twice the amount the fuse should carry. Again, there's enough time for the wiring to overheat and a piece of paper to burn before the fuse blows. This shows that even properly rated fuses and circuit breakers do not fully protect the wiring from overheating. And of course, no protection against overload would be provided if fuses of larger capacity than called for in a wiring circuit were installed. Similarly, a circuit breaker will offer no protection if it is tampered with, as was done here by tying the tripper to make it inoperative. This sort of foolishness is the cause of many fires. Now let's talk about another little understood fact. The fact that many substances normally not considered hazardous do become hazardous when their shape or form is changed. For example, this block of wood can be set afire only with difficulty. But if it is reduced to shavings, this wood can become a roaring fire. In the form of sawdust, it can even cause an explosion. Let's put some of the sawdust into this receptacle, which is equipped with 2 electrodes to produce a spark. The spark will be sufficient to ignite the sawdust when it is blown into the air by squeezing the rubber bulb. A piece of steel will not burn when a lighter flame is held to it, but the same steel in the form of fine steel wool burns. In still smaller particles, steel becomes explosive. A spark can cause an explosion when the metal powder is blown into the air. Flour will not ignite in a cup, even if the open flame is brought in contact with it. But a spark is sufficient to explode the flour if it is mixed with air. Liquids, too, become very hazardous when they are atomized, that is, broken into small droplets and mixed with air. Many of the solvents sold as safe cleaning fluids ignite instantly when atomized near an open flame. A number of insecticides will ignite when sprayed. And so will most hairsprays. Incidentally, furniture polish and waxes, which are not normally considered combustible, burn readily, as you can see. Another important point to remember: never put combustible liquids in breakable containers, such as glass. Liquids, such as gasoline and alcohol, will expand considerably when their temperature increases. The heat from the sun or a nearby radiator is enough to make these liquids expand as much as 15%. If the cover on the bottle is secured tightly, the pressure builds up inside as the liquid expands and will break the bottle. Another fact to remember about the storage of flammable liquids: An empty gasoline can must always be considered more dangerous than a full one. The vapors from just a few drops of gasoline, mixed with the air in the can, form a highly explosive vapor concentration. In a full or partially filled gasoline can, the mixture of vapor and air is usually too rich to ignite inside the can. However, at the mouth, where the vapors can mix with more air, they will burn readily. Liquids such as paint thinners, alcohol, and stove oil are more dangerous because the vapors from these materials will ignite even inside the container. The explanation is their vapor pressure is lower. This permits larger amounts of air to remain inside the can to form a flammable and explosive mixture. The same is true of JP4 jet fuel, benzol, and methyl ethyl ketone. A final word of caution. Flammable liquids continuously form highly explosive vapors, as we can observe in this shadowgraph. Vaporization takes place at the surface of a liquid only. Agitating, or pouring from one container to another, increases the area exposed to vaporization. Therefore, avoid the needless agitating of flammable liquids. In this film, you have seen why many materials must be considered as potential fire hazards. You have also learned why most flammable vapors must be mixed in proper proportions with air before they will ignite, and that such vapors are heavier than air and will seek the lowest level. In addition, you have been shown ignition sources other than a flame that can cause a fire, and how normally non-flammable substances become flammable if their shape and form is changed. Finally, you have seen why it's important to be alert when working around gasoline. While you have been watching, more than 40 fires have started throughout the United States. A destructive fire every half minute since this film began. Don't let your carelessness destroy property. Don't be the cause of your losing a home or a loved one. Remember, if you know your fire hazards, you can prevent a fire before it starts.